Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
All right, let's get going. My name's Owen Atkin. I'm the head of the plant science division in the Research School of Biology. Over the last year or so, we've been pushing forward towards creating a new centre which will allow our community to start interacting more with industry in the space of agriculture and associated technologies. As part of that, we'll have a series of workshops dealing with various aspects of that sort of ecosystem. And it's my pleasure today to be able to have a second workshop for the Centre for Entrepreneurial Agri Technology, which will be dealing with aspects here about how we translate research into practice. And what we'll present to you today, I think, are some different philosophies about how one comes at it. Those of us that exist within the ANU community often think of it from the point of view of how can I apply my fundamental knowledge to problems that exist out there, but you don't necessarily know what those problems are, and so you go looking for a problem for what you think is a solution. You haven't yet worked out what the problem is. We're going to hear an example, I think, from Alan, where from an industry perspective and CSIRO perspective, that we've identified where there's a national need. It might be, for example, how you might make an edible oil out of a plant that currently doesn't make an edible oil, and what would be the things that are required for you to actually produce that? What's the science that's required? So it's almost a reverse thinking in some ways. But we've also got representatives here from the GRDC, so we've got Hugo here, who's representing the GRDC, and he'll give you some insights into discussions we'll have later about how their particular organisation, also Will, I think from livestock, is it? Sheep, yeah, livestock. Sheep, livestock. How from their industry organisation perspectives, they would interact with researchers and deal with fundamental problems that would be, say, at farm gate, and how that translates into their interactions with researchers. So there'll be different perspectives on how one shares information, how one starts actually identifying what problems are, and how you can use your skill set. I think our overall aim is to try to sort of create an idea for you as early career researchers here at the ANU about how your skill sets might be applicable to some of those problems, and how there are different ways of thinking in terms of identifying what problems are and how one can associate solutions with those. Right? So there'll be plenty of opportunities for chat later on. So we'll start off with we've also got Liz here, who is here representing Canberra Innovation Network, which is a really important element, I think, in terms of the way in which we start changing our culture here at the ANU about how we're getting you as ECRs, early career researchers, students and so on, to start thinking about different career opportunities that might be present. And Liz can actually give you examples, I think, about how the innovation network that's growing in Canberra can provide opportunities for you to start putting your skill sets into industry context, and how you can start having conversations with entrepreneurs, different business settings and so on that exist within the ACT. So Alan, in a few moments, will give us an overview of his particular vision in terms of the problems that they face, and then we'll have a facilitated group discussion after that. And so we'll break into two groups, I think, at that point, Alan. One of them will be in the DNA room, which is go to the end of the foyer area here and turn left. So there'll be one group there. And the second group will be in the platypus room, which I think is upstairs above the Little Pickle. So it's one of those two meeting rooms that's up there. So we'll have those two a little later after Alan. And then we'll then have subsequently a facilitated discussion, which will have where we have the two groups come back together and share information that they would have discussed within their groups. Right? Have I missed something?
Well, our one special guest is Kim Blackmore from the College of Engineering and Computer Science. She's one of the facilitators as well.
Very good. And also Denise will also be one of the other facilitators. One really important element of what we're trying to do within the new centre is that it's not just biology. It's going to be biology, Research School of Biology, and emphasis here in terms of plant sciences, but also the way in which Fenner School for Environment and Society, as well as College of Engineering, Computer Science, Business and Economics. This is a cross-college initiative, and one of the key elements there, for example, is that in engineering and computer science, they have very mature programs where their students at the undergraduate level deal with industry problems. An example of that would be from their second through their fourth year, they would deal with an industry problem and they work with it in small groups over a 2 or 3 year period, right, where they unpack that problem and come up with a solution for industry over an extended period. So it's quite mature in the way in which they're dealing with that in an industry context for engineering and computer science. And there's a lot of things I think we can learn in terms of how FENA, RSD, and other sections of the university can actually start adopting that model and giving more opportunities to interacting with industry. All right, so if there's nothing else that we should maybe mention, we can maybe start with that one. Okay.
Okay, thanks, Alan. I guess it's a bit of an experiment today because you guys haven't done this before, and this is the first time I've actually done a bit of a reprise of the career that I've just completed. I've just retired recently from CSIRO, so for about 43 years, I worked across the road from here in the Division of Plant Industry, Agricultural Science Division, and more recently that's become Agriculture and Food. And so today I thought what I think Owen and Emma would like to achieve is have a bit of a conversation with you around pathways and in 2 dimensions. I think there's the idea of a pathway from from knowledge through to impact in terms of products and benefits for society. And I've got a couple of examples that I'll show you where we've applied that approach of identifying a problem first and then working out what needs to be done and going back to the science. And hopefully that will be a different way for you to experience how you do get impact in science. And the other is kind of the pathway of a career. So I'm going to map out on here how I've stepped through my career, and I don't think you should get any impression because there's a linear map going to be up here that it was in any way planned. I think you don't know where you're going to end up when you start a career, but I think it's important to be thinking about what will give you purpose in your life. Most of us, I think, start in science because they're innately interested in how things work and what we can do. Some of us also want to change the world a bit by how we can apply that science. You don't have to do that. You can have a perfectly good career in science right at the knowledge discovery area, or you can do it in translating knowledge through to outputs and impact. So I'm not trying to say this is the only way you should think about your career, but hopefully you can see how I stepped through my career, and it might be interesting to you. So pathways to impact. Well, what is impact? It's obviously different things to different people, and it's also different things at different stages during your career. So I'm not too sure of the composition of the audience. Who are students here, undergraduates or postgraduate students? Okay. And do we have only academic staff? Teaching only?
Postdocs.
Okay. Early career scientists. Yeah. Okay. So, impact for a student, you're very focused on getting a degree, obviously. So that's what I would call as an output. That's the output of what you're doing here is your degree. The impact is you want to have a job. You want to have income. You want to be able to live, So that's your initial impact. And that's what you should be perfectly focused on. As an academic, maybe the purpose for your career may be to educate the next generation of scientists, maybe to do science as well as part of the career, depending on your organisation. So it does mean different things to different people at different times. I've spent all of my career in the CSIRO, so I think probably you'll all be familiar with CSIRO. It's a mission-oriented research organisation. So the aim of its activities is to actually achieve impact. And so how does it define impact? It defines it as an effect on a change or a benefit to what you call the triple bottom line, the economy, society, or the environment. And this is beyond the contribution just to knowledge that we make through going through the scientific process. Now, I think this is a useful way, a bit of an arrow there, it shouldn't be there, to look at how we achieve impact from the science that we do up here. And throughout the talk, I'll try to come back to this because I think this might be helpful to you when you go into the breakout sessions. But the CSIRO's impact framework looks at the inputs. So what do we do? Who does what what are the activities? What's the research target? What are the outputs of that research? How do we translate those outputs into outcomes? So what changes? And then what is the eventual impact? And in CSIRO, when we look at projects, we look at it along that framework. And importantly, there's a feedback from the impacts you want to get to the inputs. And in fact, in CSIRO and in most of my career, this is the direction which we go. We look for the unmet need in society, and we try to work out what we can achieve through scientific solutions that will bring that about. So I've simplified that down to who or what's involved, what will be done in the research project, what will be created, what new things will we have, what change will happen from having those things, and what is the purpose of implementing that change. So this is the time frame for my career. Smiling now because I've just retired. But I started in 1975, and for the first, well, I guess nearly 20 years, I was engaged in plant breeding research. And then as genetic engineering came along and became to be taken up into biotechnology, plant biotechnology, got more into that space, and the last half of my career I've been involved in research leadership rather than actually doing the science itself. So what inspired me to get into an applied research agency? Well, when I was at university, this was the big thing, the Green Revolution from the 1960s into the 1970s, where basically whole populations were rescued out of potential starvation through very simple genetic changes that made the semi-fork wheats increase the yield of wheat. And this was a very simple plant breeding genetics, just reducing the height enabled a different agronomic structure on the wheat production and much higher yields. So in Mexico and in India, this really changed the productivity of those countries and self-sufficiency for grain production. And I think this was very inspiring, and it was to show that quite simple science can have quite profound impact on society. And I think that was really something which stimulated me in my last year at Agricultural Science at Sydney to focus on plant breeding and genetics. This was before any molecular biology was coming on. In fact, when I graduated in 1975, it was the first year that molecular biology was taught to first year science at Sydney University in agriculture stream. So I'm right at the end of the conventional breeding era, at the dawn of biotechnology. I came to Canberra in 1975. It was quite interesting, quite a tumultuous year to come to the nation's capital when there was overthrow of a government, and leadership of the country. It happens every second week now, but in 1975 it was a big deal. And plant breeders were actually on the currency even in those days. This is Barra, the Australian wheat breeder, and most of you won't have seen a $2 note, I suspect, out of circulation in 1988, I think. But it was very inspiring, I think, to take up a career in plant breeding in those days. And I've always gone back to be reminded that this was something right at the forefront at the time I did plant breeding, that plant breeders were worth more to the country and to society than politicians. That was a good thing to have on your wall when you came to Canberra, I think. And I've had a career which has spanned an amazing period in genetic improvement of plants and agriculture. Yes, I did look like that one day. Did have hair back in 1975. And we have, back in those days, it was very conventional breeding, just phenotypic selection. Look at the best, measure the best, select the best, cross the best, go to the next generation. And we increasingly had tools like induced mutagenesis and then gene discovery, and then looking for SNPs, variation in genes we knew, etc., in the non-GM area. But the big change has been the ability to find genes, to silence genes, to add genes, then to add pathways, and then to control pathways. So this whole increase in plant biotechnology is something which has played out in the second half of my career, and I'll give you some examples of projects we've done there. Okay, so I came to CSIRO, and as an ag science graduate, I did a master's while I was employed at CSIRO, which is something which doesn't happen very often these days, although I think there's a bit of a turnaround in that now, the engagement of industry in education. the closer alignment is a bit more like there was a situation there. So I did a master's on lupin breeding, actually, legume breeding. And then I did my PhD in oilseeds, and I did that through the School of Botany here. So I'm actually an alumni from the university here. And in 1986, I got my PhD. I'm going to talk to you a little bit after I go through this map about this project here, which is the development of a new crop, and explain how we started that project, why we did it. After that, as genetic engineering started to become more prominent, I realized that there was so much more we could do in modifying our oil plants for foods and for industrial use, but it was not something I could do because I wasn't trained in that area. So I started to build a group of genetic engineers, if you like, and appointed Surinder Singh. I don't know if any of you know Surinder from across the road, who leads the plant oils group now. I led it for this period. And we started to look at gene silencing to see how we could modify pathways in the 90s after Peter Waterhouse and Ningbo Wang discovered hairpin RNA silencing in plants, and Ching Lu did some work there on modifying cottonseed oil. And then we did two major projects in close association with GRDC around breeding a safflower, industrial oil quality in safflower, and putting omega-3 fatty acids into canola. And I'll talk about the omega-3 project mainly if I get to time. I'll also tell you about the crop biofactories projects. In that period, I was an interim director for Food Futures flagship. That helped us get these projects started because CSIRO put a large amount of investment into this space, and we use these almost as demonstration projects for plant biotechnology, particularly at the time then when the only plant biotechnology products had farmer benefits only, so insect resistance and herbicide resistance, and the acceptance of GM was pretty uncertain, and people were really looking for what are the benefits for consumers. So we decided to do some pathfinder projects, if you like, icebreakers, to demonstrate that we could have consumer benefits and environmental benefits, not just farmer benefits. And so during that period, I was leading the expansion of that group, and it's now 30 strong across the road, working in metabolic engineering of plant oil pathways. And we won't get to this today, but this is a fascinating piece of work about re-engineering plants to accumulate oil in leaves rather than in seeds, which is really prospective for increasing the amount of oil we can produce in agriculture and maybe getting into the biofuel space without impacting on our food supply. I don't think we'll have time for that today. And I really just want to start by pointing out that was in CSIRO, it's a CSIRO research effort, but a very strong association with GRDC in these projects, and with the Cotton Research and Development Corporation in the cotton oil modification, and with these two companies who are our licensees, Nuseed and Go Resources, for our GM crop products. Okay, let's go back to the first thing I did, the Lanola project. And so this is an example really of an industry setting a goal and then adopting a research strategy to try and achieve that goal. So in 1975, probably closer to 1979, when we started this project, a major problem in our agriculture was we were very heavily reliant on wheat and barley as cereal crops in our agriculture. Over 90% of our crop, agricultural crop across the country was cereals, and it was a time of oversupply of cereals, so prices were depressed. And the industry wanted to get more diversification into farming systems, both biologically, so that we weren't reliant on one crop species and the diseases of one crop species and just the general impact on the soil, for instance, but also for economic diversity, so you weren't reliant on one market. There's also a time when there was a shift away from animal fats. People were starting to realise the impact of saturated fatty acids in the diet on cholesterol, and there was a move to vegetable oil products which had much lower levels of saturates and were not considered to be much healthier, particularly the polyunsaturated oils. And we didn't produce a lot of those. In fact, we were importing them from overseas. So the concept was if we could diversify our agricultural systems to produce edible oil seeds, we would get the benefits of that diversification, and the society would get the benefits having healthier oils, and we would replace imports, so economic benefits. And so in those days it wasn't the GRDC, it was a forerunner of the GRDC called the Oilseed Research Committee and Council and subsequently. And they took two strategies, and I think this is really critical. They didn't bet on one event, if you like. There were two approaches. In Canada, this crop was emerging as rapeseed, and we know it as canola today. But in those days, it was just an emergent crop. It had been modified to have a better composition for food oils. Some anti-nutritional factors had been removed, and it was starting to take off in Canada, but we had no experience of it in Australia. So one approach was to adapt that crop to grow in Australia, to explore that. Another approach was to say linseed is a crop which we were growing in Australia for oil, but the oil wasn't suitable for food. It was too unstable for food. It was used as a drying agent in paints, basically. Could we modify the composition so it could be edible? In that case, just switch over to a new product. So I was enlisted to do this project, and the guy next office to me, Phil Salisbury, went to Victorian Department of Agriculture and started this project. I'll go straight to the punchline. Both were successful, but as we know now, canola was more successful. But I'll tell you about the linseed project. So this is just a little bit of a prelude to everything I'll say today, I guess. These are the fatty acids that are present in our oils, and I don't know to what extent the audience is familiar with them, but the saturated fatty acids, C16 and C18, predominantly present in animal fats and in cottonseed oil. The monounsaturated oleic acid, you know, from olive oil and also now from canola, and the polyunsaturates, which were present in sunflower and safflower, and linolenic acid, a highly unsaturated fatty acid that was present in linseed. So they're the players in terms of what's in the oil and how we have to modify those compositions. At this time, nothing is known about the genetics of these pathways. We have, from the structures of the fatty acids, we know what the likely steps are involved in adding double bonds in, but we don't know the enzymes, we don't know the genes. So it's flying blind at this stage. And the task for me was to try and block the synthesis of this final fatty acid, linolenic acid, and make it build up as linoleic acid, which was sunflower oil basically. Could we make linseed become sunflower oil? And so that was the project. So here's the composition of linseed oil, predominantly 18.3. Here's sunflower, predominantly 18.2. And I had to try and go from there to there. And my thesis, as a PhD thesis, looked at three areas. First was, is there enough genetic variation in the crop to just be able to find parents so I could cross and get that? And there was no variation in the species, basically, nothing below about 50% linolenic acid. So that avenue wasn't there. I spent a lot of time trying to cross linseed to some of its wild relatives, which did have the right composition, and there were very strong hybridization barriers that we couldn't overcome in those days. So the only avenue open really was to try a mutation approach. Could we mutate the genes that were controlling that final conversion and block that pathway? And so ultimately, that's the strategy. Can we block this, knowing nothing about those genes? And we just use a chemical mutagenesis approach and screen 70,000 seeds one by one using a chemical test rather than GC, and then by checking with GC. And we found two mutants which had reduced levels down to 28%. Then we had the question, are they in the same gene, same mutation effectively, or are they in different genes? Could we bring them together? And the answer to that is they were in different genes. I was able to cross them and get a complete blockage in that pathway. And so that was hallelujah day when we got that. We'd achieved the project. We've got an oil composition which is exactly the same as sunflower. And, we thought we're off to the races then, so it's going to be the next big thing. The next task was to, when you mutate, you make a lot of changes in background genotype, so we had to cross two other lines and develop the varieties to take that product into agriculture. So effectively our output from our project is the genetic trait, and then to achieve an outcome we have to develop a variety and get that farmers to grow that variety. We put a marker in there, a yellow seed colour, so we could differentiate it from that. I won't go into the commercialisation aspects of this just for time, but we could talk about that if you like. So this is, straight plant breeding. in the field, and in 1992 we released varieties in Australia. We had patents granted. We went on to release varieties in Canada and in Europe. The crop went into production, and Meadow Leaf Foods were using it to make, as a sunflower oil, to make margarine. So this is all about outputs to outcomes. And so we had this period where in the early 90s, the production of the crop was really taking off, got up to 120,000 tonnes of production, and then it stopped. So I always say beware the product life cycle, because the environment changes. And what changed here was that nutritionists had moved on and discovered that polyunsaturates were not as good as monounsaturates for cholesterol control. Polyunsaturates lower your LDL, but they also lower your HDL. And what you want is a stable high HDL and a low LDL. And monounsaturates were better at that. And so that's why olive oil has become so prominent as a healthy oil. And canola happened to have high monounsaturates. So canola was better positioned to meet the change in the market at that point in time. And so we saw this market shift here, and canola started to take off in Australia. It was a bit more promising in Canada. That was a slower change in the Northern Hemisphere, I think. But eventually the drop off there as well, and also in the EU when the subsidy situation around in-seed changed. So, but the good news story was that the guy in the next room who went to Victoria and started to work on canola was very successful as well. And canola turns out to be a great crop in Australian agriculture. And so from an industry point of view, why we did the work, the goal was met. In fact, both research projects were successful, and one of them was clearly successful, more successful in terms of the impact on the industry. And now canola is a 2.5 million hectare crop. And Phil Salisbury, the breeder, he retires this week. So we've had these parallel careers, two little boys with two little boys or something. And Phil's varieties have generated, in a 7-year assessment period, $4 billion of direct income to predominantly Victoria, but also growers in other parts of Australia as well. So I think it's a really great example of starting with a problem, going back, doing the science that you need to do, and then taking that through to the solution. And for me, my achievement wasn't the ultimate solution, but I learned an awful lot in that process, which really set up what I went on to do subsequently. So I think if you, in terms of thinking about pathways to impact, I've just tried to map out some thoughts here around that. The impact, increased diversity in cropping systems, this is what we were seeking. Increased grain exports, we now export 2 million tonnes of canola every year. Reduced import of edible oils, we now get all of our edible oils virtually, except for olive oil, from Australian production. We don't import much at all. And improve human nutrition, because we now move more and more to healthy oils. The outcome, increased Australian production of edible oil crops. We've achieved that with 2.5 million hectares, 3 to 4 million tonnes of canola now. And we did that through the research activities at CSIRO, took linseed through an edible variety, and the Departments of Agriculture adapted rapeseed to the crop for Australian agriculture. So hopefully that kind of framework is useful to you to think about that. So moving on to the next phase, in the period that I was building the group, we're now starting to work at a molecular biology level, because playing out throughout this period of probably the 1990 to 2000 period is a tremendous explosion in understanding the pathways for these fatty acids, not only how the fatty acids made, but how they're assembled onto oil molecules. And it's extremely complex, but we virtually know all of that now. And the identification of the genes involved. So compared to when I started in 75 and where we are now, where we were, say 2010, 30 years or so, 3 decades, we've gone from no knowledge about oil biosynthesis to complete knowledge, and the ability to do basically whatever we would like to do in engineering those metabolic pathways. So I won't talk about the gene silencing, but I'll talk about the omega-3 project first. If we've still got time, I'll come back to the crop factories one, because it's interesting in a different way, but we'll just see how we go for time. So this is the work of the Plant Oil Engineering Group across the road, and I've just pulled some slides from other presentations, so apologies here. But they're the three main projects that we've been working on in recent last 10 to 15 years over the road. Okay, so omega-3 fatty acids. You all know omega-3 fatty acids, the fish oil fatty acids, EPA and DHA. They're really essential for life, for health, particularly in fetal development and early growth, for brain development and visual development. Increasingly, they're seem to play a role in later life, in cognition, in mood, in anti-inflammatory responses, etc. So they're very critical in the human diet. We don't make them very well. You can make these long-chain fatty acids in the body, but you don't convert the earlier ones that we can take in the diet, say something from, say, olive oil, through to EPA and DHA very efficiently. A lot of people have diets which actually are counter to doing that efficiently, so it's virtually essential to get them in the diet, and we generally do that through fish. So the short-chain fatty acids, there are omega-3 short-chain fatty acids. So alpha-linolenic acid, the one I knocked out of BC, is one of those. But it's really these long-chain ones, C20 and C22, with 5 and 6 double bonds, which are the important ones. Now, currently we get those from fish, and you might get them either through direct consumption, or you can get them extracted in capsules. Some of them are produced, some of these capsules, from biofermented microalgal oils, pretty high cost. But there are problems with getting them from fish. Not everyone eats fish for a start. There are problems with, some people have allergies, for instance. Some people choose not to eat fish. There are problems with heavy metal contamination, particularly in the fish up the chain where they're accumulating oil. They can be also accumulating mercury in bad situations. And not all fish contain good levels of EPA and DHA. But the main problem is that we don't have enough fish. And around 2000, it was becoming a very critical issue around the collapse of global fish stocks through over-harvest of fish. And so we saw this as an emerging problem, and yet we had the ability to potentially create a new source of these fatty acids if we could engineer crop plants to produce them. So this is where we started to think about this, around 2000. For instance, it says aquaculture. You know, if you're going to make tuna, for instance, tuna is high value fish, but if you feed 2 tons of fish, you can get 1 ton of fish out there. You know, that 1 ton is very valuable, but it shows you the unsustainability of feeding fish to fish. And this was a market report looking prospectively over the next couple of decades with the expected supply from fish, wild-caught fish. And this is the demand as the population goes up and as people move to more affluent diets and are more aware of the need for these fatty acids. And there's a bigger deficit down the track. So that's the unmet need. Could we make plant sources of these fatty acids? Another driver is that, you know, if you're getting your fatty acids through fish, it's pretty expensive to get the requirement. But you're getting other food, obviously, from the fish. I'm not saying that the only thing you're getting is the oil, but you still have to be fairly well off to eat fish compared to a lot of the populations around the world. If you're getting it as a capsule, it's also pretty pricey. But if you can get it from an oil in a plant, you can get the cost right down. So making that nutrient more available broadly to the community is an objective here. So affordable, safe, and importantly renewable. They were the objectives. So this is our strategy. Fish don't make these fatty acids. They actually eat them themselves. They get them from microalgae in the oceans. And they accumulate in the fish, and then we eat the fish. So simple overview of the strategy was if we could work out how microalgae made them, we could put those genes into a crop plant, we could harvest the seeds and put the oils into the food supply in the same way. And you know, this shows probably 7 or 8 years work here in 1 or 2 slides. It was a tremendous discovery period. But basically, we were able to find and clone each of the genes involved in the pathway, 2-chain elongases, 3 desaturasses to put in double bonds to go down to make EPA and DHA. And we were able to demonstrate in 2005 in Arabidopsis that those fatty acids could actually be made in plants. Now, there are no terrestrial plants that produce these fatty acids naturally. So it wasn't known at the start whether you could actually do it. we showed that you could do it, but it was a very low level. This is not a commercial level, obviously. So the next task was to increase that. And we went back to the microalgal collection in Hobart. So this is one of the advantages of working in a big organisation like CSIRO and having access to a range of different research areas. We have the microalgal collection in the Marine Division in Hobart. And we started to look at each of the steps in the pathway, and we identified some were inefficient, some were highly efficient. And so we went looking for strains which had more efficient enzymes for the ones which were poorly efficient. And so we optimized, if you like, the selection of genes that could give us that pathway. And then in a very neat piece of metabolic engineering, we did transient expression in Nicotiana benthamiana. I don't know if anybody in the audience is aware of that. But here we could put in all combinations of these enzymes, and inject a leaf on Monday, take a leaf circle on Friday, and see which ones were most effective. And it was an incredible piece of work in terms of a combinatorial approach to get down to the best combination. Ultimately, quickly to the result, if you like, we were able to get 15% DHA in the bent leaf. And when we took that pathway combination, expressed it stably in Arabidopsis, we also got around 15%. And this is the same level as is present in fish. So we were able to get a pathway working in Arabidopsis that was equivalent to the product coming from fish, and published that. And so then the next task, was probably the end of the task for CSIRO, was to put that into canola. And then we hooked up with GRDC a little bit earlier, actually, because this is something which GRDC was very interested in for its farmers, the possibility of producing these crops, and with Nuseed as the eventual company which would take these products through the market, and started to develop the varieties of canola. Effectively, this is where we're at in 2013, engineered oilseed crops with fish oil levels of DHA. Surinder Singh, leader of the group, and this is 20% DHA. And we've gone further than that now with Nuseed. They've tested that in the field since 2014, getting ready to go commercial next year with the first DHA oilseed crop, first terrestrial source of DHA, and it's now approved by OGTR and Pheasants. So, this is the first output trait and the first Australian developed GM crop, and it's going to become commercial next year. Just a quick calculation: every hectare of canola that we grow with this trait yields the same omega-3 as 10,000 kilograms of fish. And we've also done calculations on global supply requirements when we get to 9-10 billion on the planet, and you could supply the world requirement for DHA from the global canola crop. So, that's the way we go, particularly if we go into direct consumption of these in the food supply. We can meet future needs renewably from this source. And that's the team, the main omega-3 team at CSIRO. I might skip over this, but if you're interested to come back around translating outputs to outcomes in the GM space, this is a really difficult area because there's a lot of things you've got to get right in terms of freedom to operate, as you'd appreciate with the IP protection, permission to operate in terms of the industry. Can you control the trade? Can you steward the trade? Can you prevent any trade impacts of having GM crops in a non-GM agriculture? And a whole range of issues there. Worth exploring at some stage. So I've tried to map that back here again onto this framework, and so the impact we were seeking, or the industry was seeking, and this is not actually an industry coming to us and saying this is what we need, because there is no industry for this really. The fish industry supplies this at the moment, and they're struggling, but they're not the agricultural sector. So this is us understanding what are the major drivers playing out. And an important element here was, is this a sustainable nutrient, or is it a fad? Interesting nutrients goes up and down, and some things are flavour of the day, and a few weeks later, they're proven to be not. We had done a lot of research on omega-3s in CSIRO since the early 1980s, and we knew about the impact, particularly on cardiovascular health. And by the time we got to 2005 and started this, it was stable. Everybody knew that this was definitely a nutrient of importance and it was unlikely to go away as a fad, so we could commit to it then. So new sustainable sources of omega-3. Higher value canola crops, that wasn't something of interest to the industry because these oils are more valuable than traditional food oils, so that we expect to get higher returns for farmers who are growing these crops. And importantly, when we started the project, this is an example of consumer and environmental benefits from GM crops. We wanted to change the debate at the time we started this project by doing kind of a landmark project with consumer benefits. And it's going to be very interesting to see this play out now in consumer acceptance. The outcomes, farmers growing DHA canola crops in Australia and globally, and DHA canola used in agriculture feeds and human foods. And then, what CSIRO did and what Nuseed did and the important role of GRDC in bridging that gap from research to commercialisation in co-investing with CSIRO. So, they're two projects that I've had quite a lot to do with in my career. But look, going forward, ongoing challenges, they're just as big now as when I started. Food security is not going to go away. We're going to have 2 billion extra people to feed. We've got climate change, so it's a challenge on our agricultural systems. And we've also got the issue around where do we get our energy from renewably and without impacting the climate change issue through continuing to dig up fossils. And I think this is really important going ahead. We have to solve all these problems together. You can't just solve one of them. You have to solve all of them. So I think there are many challenges for science and technology going forward. And if we had to end here, that was going to be the closing slide. I'm going to challenge you guys to think about your own research and what might be your pathway when you eventually leave university and take up a research career if that's what you do. I think we do have time to give another example. So I'm going to talk about crop biofactories. So at the time we started the omega-3 program, it was about 2004, 2005, we had a significant engagement with GRDC around prospects of starting a bio-based industrial economy. In other words, could agriculture not just supply food, but could it supply raw materials for fuels and more importantly, in that stage, for chemicals, to replace petrochemicals. And this is a case where we worked very closely with GRDC in shaping an initiative. There was a lot of early work done, workshopping around what should it focus on, and what crop should we work on, what should be the targets we went for. And eventually we formed this Crop Biofactories Initiative, which was 50% funded from CSIRO and 50% from GRDC, and it went for about 8 years. And we started off very broad in terms of the traits we looked at to see which ones might be feasible. And then at the same time we did market analysis to work out which ones would be valuable in the market, and then we kept narrowing down the portfolio to focus on one particular trait. And I'll step through that for you. So this is my little graphic that I just like to point out where we are with carbon in the atmosphere going up and up. We need to bring that down. One way to bring it down is to start using that carbon to feed our industrial society and our standard of living rather than keep taking it out of the ground and putting carbon into the atmosphere through traditional means, petroleum. And plants can produce a lot of the products that we produce from petroleum these days, either directly or by subsequent conversions. GRDC was particularly important in focusing on which crop we would go for as an industrial oilseed, given that we have food oils out there, and we're going to grow another crop which is going to go for industrial use. It may not be suitable for use in food. We may have to segregate it from food. So which crop is best positioned for that? And we decided on safflower because it was a crop that was a food crop, but it was a very small food crop, and it was able to be grown particularly in the north where farmers urgently needed alternatives. So a lot of thought went into that. I won't go into a lot of the detail, but safflower was chosen. It was also very technically suitable to modify. We could transform it. All fatty acid genes had been cloned. We had promoters available for expressing genes in seeds. It had some favourable starting oil profiles. All the genomics were starting to be available, and it had been released overseas as a GM crop as well in USA, and was at the time being considered for a source of insulin production in Canada. So a lot of things pointed towards that. And the molecule we decided to focus on was oleic acid. So this is 18-1 from the earlier stuff I showed you, the main component of olive oil. This is interesting chemically because it has a double bond in the middle. You can break that and produce 2 C9 units, which can be then used to make things like bio-nylon. So we had quite a bit of industry interest in this product, and we thought it's an ideal starting product because it's in our food supply. So if we can make a very rich source of this fatty acid, almost like a chemical feedstock rather than a mixture of fatty acids, we can grow that in our food agriculture without any risks. And that's the way it's turned out. It's highly stable fatty acid, so if you have an oil which is very rich in this fatty acid, it would be ideal for use as a lubricant. Direct use in biolubricants, you could break it up as an oleochemical precursor. High human safety, biodegradable, high stability, very favourable. So we started with the same pathway. In the case of safflower, there was the original form of 2 forms of safflower present in nature. There's one which is high in linoleic acid and one which is high in oleic acid, but only 78%. And this is high, but not high enough to be a chemical feedstock. You have to have virtually pure feedstock, and really the target was 95% of this fatty acid in the oil. So this is the first use of hairpin RNA gene silencing. We're able to, at this stage, we knew the genes, and so we were able to design silencing constructs against those 2 genes, particularly this one. This is kind of stopping some of the palmitic acid from going straight to oil and sending it down the pathway, and this is stopping it being converted to linoleic. So we tried to maximize the accumulation here. We did it, express it seed specifically using a particular promoter, and in fact that's what happened. So we got 93% oleic acid content, and we've now got higher than that. And this is the product that we were after, and you can see from the GC trace it's virtually a pure chemical. Now there's some serendipity here. We tried this in several other species at a research level before we tried it in safflower, and in no case did we get above 85%. Safflower turned out to be, for some reason that we don't yet know, very amenable to this change. So, the guidance from PRDC in landing on that crop also happened to be, very critical in terms of the result. Anyway, that's the serendipity. If we tried to do this in canola, we wouldn't have the product today, I'm sure. So we've taken that material out to the field, and the transgenic crop, the seeds germinate normally, even though they have this very unusual oil, same as the null segregant. We've grown it in Kununurra, and we get bountiful harvests of seeds. And so this is now sitting up here as a super high oleic, we call it, safflower. Its stability is 4 times the parental type with 78% oleic acid. It goes up enormously as you get rid of the polyunsaturates. We've tested it. We've had the bosses out to have a look at it, and Go Resources have been set up as a company. So in this case, we went out for expressions of interest. This is a smaller opportunity. This is probably something like 100,000 hectares. And safflower is not a crop that the big players were really involved in. So there was not a conventional path to market with the ag biotech. So we thought it's probably going to be a startup. And the startup did form to take this technology to market. And Go Resources has got the license for exclusive rights to this in Australia and internationally, and I haven't put it up there, but that is also now approved by OGTR and Fazance. So same timetable, almost at the same time now being considered by the regulators, and both positive outcomes. We now have 2 new GM oilseed crops going into production in Australia shortly from the work of CSIRO of the group and GRDC in co-investing with us on that. I don't think I've filled this in. No, I haven't. But I think you could go back and think about that project from the same perspective. That might be an appropriate time, Alan, to.
That's excellent.
Stumpson, see if there are any questions.
Thank you very much. Maybe we've got time for a few questions, I think, directly in terms of what you presented. And thereafter, we're going to have a more facilitated discussion. Is there anything specific in terms of what you've heard you'd like to explore?
Great insight for you. So I just wondered, like, we feel with the safflower and the canola now being GMO particularly regulated, accepted, what's your view on GMO being more the push and emphasis over traditional or even CRISPR type method?
Yeah, well, I have to say that when we started those projects, it was very uncertain as to whether they would be accepted eventually, because it's in a 10-year time frame. And we had some of our trials of genome were attacked by activists, for instance, and so my personal belief is we haven't done enough along the way to bring the community up with what the benefits can be for the technology and the safety of the technology. In fact, there's a microphone on. I want to go as fast as I say. I think we could have done more along the way. But what was very interesting is I think it has died down a bit since those times. We did not have in the public comment phase right of those crops any significant opposition to. Now maybe that's because they're not being seen by those who are opposed to the technology in terms of agribusiness control and Monsanto, Bayer dominance, that sort of thing. They're not seen in the same way because those players aren't involved and these are not farmer-only trades. Maybe that's being seen, or maybe the opposition is going down a little bit around that. So I still think we won't know until the products are out there for sale what the reaction will be.
So given that the opposition is going down, what are the funding bodies like GRDC and all that, they teetering in, as in you're going to be more accepting of pursuing these type of funding, these type of...
I don't know in terms of what the current attitude might be, and perhaps you can get a comment on that, but at the time we started that, they were on board with us in terms of we need to demonstrate the benefits and we need to be advocating the technology rather than sitting back and letting the other voices dominate and shape consumer opinion, I think. So I think certainly they were alongside us in both of these projects for the last 7-8 years and wanting to see the outcomes and getting into agriculture. We're in a very interesting period now with gene editing and whether gene editing will be considered to be GM or not GM. But if it was to be not GM, I think there's still parts of the market. It's really a case of gene editing opens up innovation because it allows you to do things in a very simple way, and you perhaps don't need, if it's not regarded as GM, you won't need the big investments required for deregulation. And so it's kind of a democratization element to gene editing, I think.
If you want to add to that from the GRDC.
Yeah, well, the things that the GRDC, the definition of the GRDC is that we are technology agnostic, so it means that we will use any technology that is available to reach our goals, which is improving farms' profitability. So that means that if the GMOs are a tool that is available in terms of technology, but also in terms of regulation, then we are fine with that. I think that because the path to market of these products is usually quite complex because not only because of regulation but also IP and these things. So we usually traditionally at least in any project that involves the development of a GM crop, we require to have industry backing up the project, right? And generally the kind of companies that would participate in these projects were multinationals. So yeah,
and I think we wouldn't have gone the next step after the kind of proof of concept without that, and that's when GRDC came on board, and that's when we started to work with UC. We did need that investment to be able to mount the regulatory package. I should say it's not as expensive as you might hear from the major players, and so there's very much an element of boosting that number as a barrier to entry. I think, our experience from going through this is it's not the sort of figure you see in the literature. It may be for global, but if you can do on a regional basis and manage the stewardship of the trade, then it's something that's achievable for a mid-range company.
Barry, you talked about the double bottom line with high DHA canola. The messaging with the Marto City with the City vegan towards the health environment and also just healthier versus GM. I'd be curious to know as to what jokes aside, I'm curious to know as to what market research you did to see how that portion of the market would respond to a product like this, and what sort of marketing you would do in the future to help drive acceptance of that person to understand the environment and health-driven choice.
Yeah. So when we started the project, we worked at a very general level on that question. We did some consumer marketing from our group in Adelaide, our human nutrition group, around attitudes to GM products that had consumer benefits without being specific around them. And we monitored that for some time in the Food Futures flagship, and it was fairly encouraging around the receptivity to that message. As we've got down to a specific product, and then you have commercial considerations around when's the right time to have that discussion with the community. We haven't, on the CSIRO side, gone back into that space. It's really for our commercial partners to manage their marketing and that engagement. And I think we'll see that happen now that we've passed through deregulation. I think it's a case of, I think, not having everything boiling at the same time. And so we've got the science-based analysis and the deregulation step through, and now the challenge is for them to work with the marketplace. And,
do you think that's appropriate that the commercial partner can control the marketing when CSIRO, both in terms of this product and future products, has a real vested interest in how the marketing is done?
It does, and I don't think it's inappropriate. I mean, they're actually paying predominantly for the project in a major way, so you have to respect that. I think there are a range of interests that all the players have, and you have to work a balance on that. Now, if we were sitting back as an uninvolved party and just commenting on other people's technologies, that's a different position to be in. I think you have to be able to work sensitively with all the parties in the project if you want to reach a solution. And so, it's a difficult thing to manage through, but I think it's okay. I understand exactly the point you're raising. Yeah.
When you're giving the talk about the modification of fatty acids in seeds, I was thinking actually also of work that had taken place at the University of York by Ian Graham's
Yeah.
and that was using a tilling approach. And that was, I think, because the Gates Foundation was trying to find a way of producing these, which was not in the GM context. So you've done it in a way which is using a crop which seems to be accepted, I suppose, in a genetically modified context.
Yeah, so the tilling will help you uncover or create variants in genes that are already present in the species. So it's a way of directing your mutagenesis, if you like. You can find either natural variants, or you can go and select specifically for a change in a particular target gene because you know the sequence of that gene now, or a mutation, and see if that gives you the trait you want. And so for some projects, that's a suitable approach, and so it's a more precise method, and that's really at the top end of the non-GM arc that I do at the start. But in our two projects, we couldn't use that. The first reason is that for the safflower project, quite simple change, we didn't want to mutate that enzyme globally in the plant because the polyunsaturates are necessary for membranes. I'm sure you all know that. They're main components of membranes, and so you don't want to switch off the production of those fatty acids in leaves. You have agronomic problems if the crop suffers from that. You just want to switch it off in the developing seed where it's storing the oils for germination. And so by putting in a gene and directing its synthesis with a seed-specific promoter, you can control that and leave it switched on throughout the rest of the plant. So we couldn't have tilled for that. And then obviously with the omega-3, there's 7 new enzymes that aren't present in the plant. So, you can't create that by modifying genes which are already present in the plant. Not easily, anyway.
So CSIRO, Alan, is a really unique organisation and very different to ANU. Part of the remit of investing in something like CEAT from the ACT government is to enable more of these stories and spin-outs in particular to happen. What do you think are some of the institutional settings that might be barriers to enabling that, and how do we address it?
Well, I don't know that I don't know that there are barriers. There might be culture. I meant to mention that when we went back upstream, particularly in the omega-3, we needed to access information from a whole range of places. So the unraveling of the pathway to DHA in microalgae was not just our own work. There's universities around the world who are doing work to discover genes. This is all coming together from the scientific community, and we're piecing that information together. And in some cases, we're doing collaborative projects with particular university groups that have expertise in a particular aspect of that work. So CSIRO does reach out at a research collaboration level, and that's been part of our strategy in the last 10 years, was to develop more of that in terms of collaboration hubs. Really there's a strategy and then operationalizing is the issue. So it comes down to the connections between the scientists, I think, in a large way, who they reach out to work with. But I don't think it's an impediment to working collaboratively between CSIRO and universities. It's finding a project and finding the people who, the project that needs that, and the people who are open to that on both sides of that. But structurally, no impediment. I guess you have a different funding model to CSIRO. That's one element. In that we couldn't have done the omega-3 project except that CSIRO had a major flagship initiative and brought resources together, and we actually reshaped a whole area of the organisation around demonstrating the ability of science and technology to improve the supply chain in agriculture. And this was right down the chain, and this particular thing was way up at the crop level. So we had this mobilisation of resources that we could apply to a new project area. And, that's a bit more difficult to do across organisations than within an organisation. So some of that, we had a collaboration fund as part of that, which was for university collaborations with CSIRO, and that was used as part of the flagship program. But maybe I could flip it around and say, what do you see on the other side of the fence as the challenges there?
I think the main thing I was thinking about when asking the question was having a stable research team over decades.
Yeah.
And that can be hard to achieve in the university.
Yeah, and that's exactly what we've had here. So that goes probably to the point I talked about the quantum, but also we've had that resource for 8 to 10 years to do that. And I was reflecting on that with one of my university colleagues recently from overseas, and one of the frustrations our scientists have in that group is that because we're so applied, you'll do a piece of science and you want to do the next piece, you want to understand that result, and you want to get the paper in Plant Journal or something around that, but you have to go on to the objective and adapt and try something else. And so there are all these unfinished pieces, which inevitably mean that other research groups, predominantly in universities around the world, will pick those ideas up and will do that as a thesis project or something, and we'll get the great publications. So our guys often don't get the great publications because they're going on to do this work. And I was kind of bemoaning, the problems of working in CSIRO from that perspective. And this colleague's university professor in Vancouver, UBC, and she said, well, you've got it great because I get an idea and a student runs the project and is going to leave, and I know what to do next, but I've got to wait till I get the right student or the fund to do that project. Have no continuity. So we can have continuity and commitment, and I guess that's a problem on the university side. It is a different environment, and it's a challenge for us in CSIRO because our scientists have tended to be judged for their promotion prospects around their scientific output, and getting the organisation to change to recognise the applied outputs above or equivalently to the scientific outputs.
And maybe on that one too, I think it's worthwhile, think about what your assumption might be if you go into an applied space. My assumption was the impact of your work through publications would fall away as the impact rises and these societal outcomes and so on. You couldn't have your cake and eat it too. But my discussions, like sitting down with John Manners and so on, was that actually there are individuals within CSIRO who, through their applied outputs and so on, had papers in Science and Nature and so on, the initial discovery of the mechanism, the second part about the application and so on. And in fact, some of the metrics in some of the areas there are extraordinarily good, with the number of highly cited researchers actually that occur within that fabric. So it isn't a case that the applied element necessarily leads away to a loss of that research impact. The second thing I think also you mentioned earlier was about the fact that scientists need to meet and so on. One of the key elements probably for making it work for the ACT is for getting CSIRO staff and ANU staff and students to mix. Literally, that sort of serendipity of the cafe we have here has created a wonderful networking place for people from FENA, chemistry, biology and stuff, who never used to meet, now meet. And we've got to find vehicles like that that are going to bring CSIRO and ANU staff together regularly, so they get to know each other. And then just by a couple, you're talking about what you might be doing, and someone picks up one of those things that you can't follow anymore, and then takes with it. But at the moment, they're not happening as much as they could. So that's our challenge, is trying to find the social networking elements that will be.
Valley of Death, as was mentioned at the following.
So in that sense, co-location was a really important thing. One of the reasons why new centres being formed with a hub and so on was because about bringing us together in one place for a project that was a core element of what was being done from that point of view. So
I think I still go back to organisations can do a lot to bring that about. It's going to be driven by people, and it's really about the people who want to reach out and work together that really make that work, I think.
But understanding the business models is useful. 80% of your funding comes from external industry sources, and that means that you have to work towards those targets. We work in a completely different business model, and it does not say it stops the barriers are a bit there, but a bit of understanding the business model can help you then appreciate the pressures that each other are under and find a way around it. So being naive or completely unaware of that business model probably just will lead to friction, because you think, why can't they behave like my colleagues around me at this institution? Now, we're going to move the next 10 minutes, I suppose, I think, to a more facilitated discussion in groups. Emma, do you want to set up something in the context of that before we go off into two groups?
No, not necessarily. I mean, we set a question before today, which was, what is an example from your group of a potential real-world farming application from research currently being undertaken? I guess we're just wanting to have smaller group discussions to explore that idea, to just hear a little bit more from each of you about what your research is currently. Do you see it having any sort of potential to be applied? Has that evolved through time, or did you set out with that applied question in mind? And then we were just going to come back together. I've come up with a clustering for the two groups.
And those groups will be mixed, in the sense that you'll have people who won't be just like you, in the sense maybe as a student or a postdoc working on a particular subject. Often you're going to have people from different industry contexts and different types of diversity with you. So I think it would be very good in your discussions to get a sense of, in the sheep livestock sort of space, how does that industry interact with producers and with researchers, the GRDC as well. It would be really useful for you to be able to get a sense of how those different organisations work up, work down, and then that may also inform a little bit about where you in the future might be able to fit in. And one of the key things I think about it also, when you understand that fabric about how GRDC and the livestock space operates, you might find that opportunities for yourself in the future just because you start to understand how it's framed, right? From my perspective of the GRDC, that was crucial. It was actually starting to first working out how you interact with researchers and how we could put an idea in front of you. Now, that operates with the Gates Foundation, right? With the Gates Foundation, it's about how do you actually start putting your ideas in front of that Gates Foundation for them to influence what their future decision-making would be. And I presume that's the case in a number of the RDCs, that you put an idea there and they may start working with it and come back to you as a supplier of that particular work and so on. So it's very good, I think, that 40 minutes to have a bit of a chat where you try to understand how the research development corporations and so on interact, both up, sort of upwards and downwards in the way in which they're interacting with the producers and researchers. So we've got one room up there, one room up there. Does anyone not know what group you're in? There's an email. Emma, she will be able to tell you. Group, which one? Group 1 is in which room?
So group 1 is in the DNA room, and that has Jason, Michael Rosman, and Chris, Sonia. Now I don't know everybody's names, so I hate reading these out. Yihang, Kim Blackmore, Will Oldfield, Owen, and Alicia. So you're all in group 1 in the DNA room. So, but I'd also say it's just meant to be an organic, relatively unstructured.
There is a structure and the facilitators have got it.
Okay, yeah, all right. And so that leaves in group 2, Reshmi, James, Lily, Brad, Sally, Liv, Hugo, Barry, and myself. And we're upstairs in this group.
Right, very good.
I don't know, Alan, if you wanted to.
Just want to get this out of the.
Oh, that's terrific.
I hope it was
It's got
reasonably what you
enjoyed the
wanted.
science. I enjoyed the light elements of it. It was all great.
Just, I'm not sure where to clear it, but.
Just wanted to make sure it's
Yeah, I think the pathway is useful to